Good afternoon, everyone. So this is the second of my lecture. As yesterday, I will lecture for something around 1.5 hours, which in my opinion is the maximum that can be spent for a lecture, especially one online like this one. And so I realized that it's more difficult to make questions using the system. But if you would like to make some questions, please do. And also, yesterday I realized that I got a perfect number through the chat, but I only realized after the lecture was finished. So if you have some other questions, please stop me or ask to stop me so that I can listen to your question. I think that's useful for everyone. Okay, so I'll start by sharing my screen. That's it. So that's it. So yesterday, we were talking about the following theorem. So let d of n be the number of positive integers such that d divides n. See, so this is the number of divisors function, so that d of a prime is 2, d of a power of a prime is alpha plus 1, and d is multiplicative. Which means that d of n times m is equal to d of n times d of m if the GCD between n and m is 1. So these are some properties that we observed about the divisor function. But the theorem we wanted to discuss here is the average. So Dirichlet and the statements is the following: is the sum for n less or equal than capital X of d of n 1 over x. So this is the average of the number of divisors of integers up to a bound x. This is log x plus a certain constant, which we're going to write as 2 gamma plus 1, plus a certain error term that depends on x. And so if I write it like this, I haven't said anything yet, right? Because the e of x can be anything, but the important fact is that e of x is bounded, so it's less than a constant times square root of x to the minus 1, as x tends to plus infinity. Okay, so this is the statement that we would like to discuss today. And I think it's, before we get into the proof, I think it's important to try and appreciate this statement, what it tells us. it tells us that sometimes this divisor function can be very small, can be as small as 2 when n is a prime number. Sometimes it can be a little larger, right? For power of primes, it's that power plus 1. And when I'm testing it on a number which has a lot of prime divisors, then this divisor function grows and grows, right? But on average, is always the log of x plus a certain constant. Sorry, I made a mistake here. This is -1. Oops. It's always the log of x plus a constant with an error term that tends to 0 in this fashion. So before I go on, I just want to change the notation a little bit. So notation. So we say that a certain function of x in this case is equal to O of g of x if f of x is bounded by g of x. Okay, so this is a different way to write the same thing, right? But sometimes it's useful to use an equal sign to do the computation. So in using this notation, so the Dirichlet theorem can be stated in the following way, that the sum for n less or equal than x of b of x is equal to x log x plus x times 2 gamma minus 1 plus an error term of the order of square root of x. So I'm sure you can identify these two statements as being exactly the same one, just using a different notation and multiplying everything by x. Okay, and so we had this lemma. Oops. This lemma, which has also an interest by itself, and it gives us like an asymptotic formula for the harmonic sum n less or equal than x of 1 over n. We know that this is the truncated series, the truncated harmonic series, and we all know from our first or second year calculus that this series diverges. But what this lemma is telling us how it diverges. So it diverges in the following way, as log x plus gamma, and then there is an error term, and this error term tends to 0 as 1 over x, where gamma is by definition the constant that I obtained taking 1 minus the improper integral between 1 and infinity of was the fractional part of x. So t minus the integer part of t over t squared dt. And so the first remark is that gamma is well defined. Why is it that well defined? I mean, we're defining this constant through an integral, through an improper integral. And we all know about improper integrals, that sometimes they converge, sometimes they diverge. sometimes they simply oscillate. Now, this is an integral of a positive function, right? It is defined via an improper integral. And so in order this to make sense, we have to check that the integral actually converges. It converges since when we take t minus the integral part of t, and we always denote this by the fractional part of t, this is always less, it's actually strictly less than 1. Hence, sorry. The integral between 1 and infinity of t minus the integer part of t over t squared dt. This is certainly smaller than the integral between 1 and infinity of dt over t squared, right? So, which means that this, we know that it converges. Actually, we also know how to compute it, right? This is minus 1 over t computed between infinity and 1. Okay, so, and this is actually 1, right? So the integral is smaller than 1, and it converges. And this implies, of course, that gamma is bigger than 0, and it is well defined. Okay, and gamma is called Euler-Mascheroni constant. Sorry, my pen doesn't work very well. You have to be patient and decrypt my writing. Okay, it's the Euler-Mascheroni constant, and this is actually, it's a constant that appears in many different places in number theory, and if one computes the integral using some numerical methods, one can also approximate the constant. And actually, if you do it, or if you ask some computer to do it, then you may find out that this constant is 0.5772156649 ... And so the Euler-Mascheroni constant, I'm sure you will meet it again next week when Michel Schmidt will talk to you about the Riemann zeta function. And it's a mysterious constant, which is defined through an integral. And it appears both in the approximation of the harmonic sum and also in the Dirichlet theorem for the divisor function. And one open problem is the following: is gamma a rational number? This is not known. We don't know whether this number is rational. This is, well, the guess, if it's that it is not rational. So I guess the guess is that gamma is not a rational number, but no one has been able to prove it so far. So you see, it's a simple problem to state, relatively simple, but still unknown. So let's go back to the sum of 1 over n less or equal than x equal log x plus gamma plus an error term of this type. We deduced it from the partial summation formula. Okay, so the partial summation formula, it's the following identity. So we're taking a sequence of complex numbers. We're taking a function which is C1 in, well, I think between 0 and infinity. I think I said between 1 and infinity, but I mean, it has to be C1 in the region where I need it to be C1. And the identity is the following: the sum for n less or equal than x of an f of n. This is equal to f of x times ax minus the integral between 1 and x and f prime of t, a of t dt, where a of t is simply defined to be the sum for n less or equal than x of a of n, a sub n. So this is the partial summation formula. And so star, which is this identity, star follows from partial summation formula with f of x equal 1 over x and an equal to 1 for all n. So if you plug in this data in the partial summation formula, you get exactly star, this identity. Okay, so now let's give some proof of the partial summation formula. So let's see how it comes. So let's start from oops, sorry. Let's start from this integral between 1 and x of a of t f prime of t dt. Okay, well, a of t is, so it's the sum for, and is constant piecewise, in the sense that if we have to draw a graph of a of t would be constant on integers. On stretches would be constant on stretches of length 1. So this is what I mean by piecewise. So if we, right, because if we is 100, then A of 100 is equal to A of 100 plus 1/2, right? Because simply because between 100 and 100 plus 1/2, there are no other integers, right? Sorry, my pen is always giving me. I used to have a better pen, but I cannot find it no more. Okay, so by this simple observation, right, we can write this as the sum for n that goes from 1 to, say, the integer part of x minus 1 of the integral between n and n plus 1 of a of t f prime of t dt. And then I have to add a little tail here, which is the integral between the integer part of x and x of the same thing. A of t f prime of t dt. So I decompose that integral as the sum of these integrals. And if t belongs to the interval n plus 1, then a of t is simply equal to a of n, right? Because there are no more integers between an n and n plus 1 strictly, right? So the integral between 1 and x of a of t f prime of t dt can also be written as the sum for n that goes from 1 to integer part of x of what? Of a of n, because between n and n plus 1, a of t is a of n, and it's constant, right? And then the integral between n plus 1, sorry, n and n plus 1 of f prime of t dt. And then there's this last bit here, which is going to be plus a of the integer part of x, which is the value on this last interval of a of t, and the integral between the integer part of x and x of f prime of t dt. Right? At this point, we can use the fundamental theorem of calculus, which tells us that the integral of f prime dt is equal f of t plus a constant. So this is the fundamental theorem of calculus. So we end up having that the thing above here, it's the sum for n that goes from 1 to the integer part of x of a of n. And then there I have f of n plus 1 minus f of n, right? Plus a of the integer part of x times f of x minus f of the integer part of x. Right? Now, let's see what happens here. So there's some cancellation. Let's write the first terms of this. So I have A of n can also be written as A of n plus 1 minus A of n plus 1, right? So this is the sum of an up to n plus 1. If I subtract the last term, all I get is an. So I can take this identity and plug it in here. So if I do this, there's a lot of cancellation, because what you will get here, you will get the following. You will get the sum for n goes from 1 to integer part of x of an plus 1 times fn plus 1 minus the sum for n from 1 to the integer part of x of an plus 1 times f of n plus 1. Then you will get a minus the sum for n that goes from 1 to the integer part of x of f of n times capital of A of n. And then I have, you see, and then I have the whatever is left, which is plus f of x times A of the integer part of x minus f of the integer part of x plus, oh, yeah, no, sorry. Times A of the integer part of x. So you will see here, there's a lot of cancellation, right? Because most of the sum, let's change the color here, yes. Most of the sum will cancel with this sum, right? Almost everything. The only term that will not cancel are, I guess, the last term of the first and the first term of the second. So what will be left here will be A, oops. So A of the integer part of x plus 1, f of the integer part of x plus 1. Okay, this is in the first sum, but not in the second sum. And then minus the first, so I have a f of 1 and then A of 1. And the rest will cancel, right? And then here, what I will have, I have still minus the sum for n goes from 1 to the integer part of x of an plus 1 times f of n plus 1. And well, and then I have a plus f of x. So was that a plus? Yes, I get, yeah, plus, and then A of the integer part of x is the same as A of x, right? Those two things are equal. And then I have a minus f of x A of x. And now you see we're almost there, because if we rescale the sum, then this sum starts from n equal to 2, right? N equal 1 means n plus 1 is equal to 2. So here I can add this to this, and it ends with the integer part of x with a minus sign, right? So I can have the first term here, and I should remove the last term here. So this is finally the above equals simply minus the sum, n goes from 1 to the integer part of x of an times f of n. And then, so this, when I do this, I have removed the last term through this and added the first term through this, right? So I have this, and then I'm left with the plus f of x times a of x. So we arrived here starting from the integral between 1 and x of a of t f prime of t dt. So if you change sign and bring f of x, a of x on the other side, this completes the partial summation formula proof. Okay, so the identity 1 over n less or equal than x equal log x plus gamma plus an error term. This is established. So now, you know what, I want to change my page, because otherwise it happens what happened yesterday, that it will remove part of it. So I am on a new page, and so let us sorry. Is there any question?
No question yet, sir.
Okay, thank you. Let us go to Dirichlet theorem. So we want to deal with this sum, the sum for n less or equal than x of d of n. So this is the object of interest, right? There was a 1 over x which I brought on the other side. So we can write this as in the following way, as the sum for n less or equal than x and the sum for d dividing n of 1, right? So this is the way of writing. These two sums are the same, right? And so if d divides n, this means that n can be written as a times d, right? And so for every n up to x, we count the number of d such that n can be expressed as a times d. For each A and D, there exists a unique n, right? If we fix A and D, there's a unique n. So we can write this just because of this observation, we can write this as in the following way, as the sum of all pairs A and D natural numbers such that A and D, they're both less or equal than X. And the product also is less or equal than X. Counting the n's, it boils down of counting the pairs A, D such that the product is less or equal than X of 1. So it takes a bit of time to agree with this, eh? Agree with the fact that these two are the same. So you should think about this. But once you convince yourself that it is correct, then everything becomes very different, right? So we are counting simply pairs of integers A, B that lie under the hyperbola S times T equal to capital X. So I can make a drawing here. So this is the plane ST. This is the parabola, which is equation S times T equal to capital X. And what this formula is counting is all the points with integer coefficients which are below this hyperbola. So we need to count these points. The points which are below this hyperbola. And the question is, what is the best way to count these points? So, well, one thing about this hyperbola that it is symmetric, right? There is a symmetry here. So there is a symmetry. With respect to so the line S times S equal to T, right? So all the points here, the number of points here is equal to the number of points here. So if so let's see. No, I shouldn't make some tests here. So the number of points here equals to the number of points here. This is pretty evident, right? So, well, there is a reason for this symmetry. The reason for the symmetry is that if a divisor, if d is an integer that divides another integer, then automatically I have another divisor. N over d is also a divisor of n, right? So whenever I have a point here that divides this, so a pair of points, so these are a pair of points S0, T0, such that the product is less or equal than x, then I have another point here, which is the point T0, S0, which enjoys the same property, right? If S0, T0 is less than x, then also T0, S0 is less than x. So this is testified by the symmetry, okay? And so the idea of Dirichlet to count the points below this hyperbola, in fact, this theorem or this method of proof, which is a method which is used also in other problems, it's called the Dirichlet hyperbola method, okay? So his idea was simply the fact that, so the sum, so the idea is the sum of d of n, n less or equal than x, equals, well, first of all, we count, oops, sorry, I want to make a good picture here. First of all, we count the points above. So we count the points above. So these are the green points. And then we count the points below and we add them up. So we can count this, and this is equal to this. So this is equal to twice the point above, right? So it's enough, we count them. Now, it turns out that there's even a better way to count them. And the way to count them is to isolate the points in this square. Oops. To isolate the points in this square and write the following, that this is equal twice the points in this region. So I count twice the point in all this region. But if I do that, then I've counted the points in the square twice, right? And so to this, I subtract the points in the little square. So this is the way to count them. So count twice this integers below this piece, and then subtract once the points on the square. So I have a little question for you. What are the coordinates of this point here? Well, the coordinates of this point is the point in which s times t is equal to x. So the coordinates of this point is the square root of x times the square root of x, right? This is that point here. So now I have everything to set up explicitly my sum. And the way to write it is the following. This is equal to twice. And so that is the sum. Well, let's see. So these are integers. So n goes from 1 to the square root of x. And for each fixed n, so for each fixed n, I have the sum. Okay, for each of this, I have the sum of 1, and 1 goes to from 1. So m goes from 1 to x over n. Sorry, I'm gonna fix this. So this is something that needs to be stared, right? So n goes from 1. I remind you, this point is the point of coordinate square root of x, square root of x. So n goes from 1 to square root of x, and for each fixed n, this point has coordinate x over n, x over n. Okay, so for each fixed n between 1 and square root of x, I have to count the number of integers on this vertical line. And then I have to subtract the point on the square. But the point on the square are simply, so there's going to be squared, something squared. And here, there's going to be the integers between 1 and the square root of x. Okay, so this is a way to write differently the average of the divisor function. And now here, I can do some manipulation. So how do I do the manipulation? Well, simply this is equal to twice the sum for n between the square root of x and 1. And so how many integers are there between 1 and x over n? Well, this is just the integer part of x over n. And then here I have to subtract. How many integers are there between 1 and the square root of x? Well, this is just the square root of x squared. So from here, I can write that this equals twice the sum for n less or equal than x, the square root of x, bigger or equal than 1. And what this is equal, this is x over n plus, or actually minus, the fractional part of x over n. And this is equal to the square root of x minus the fractional part of the square root of x. So this equals to twice the sum, well, twice x, the sum for n between the square root of x and 1 of 1 over n. And then there's a minus twice the sum for n less or equal than the square root of x, bigger or equal than 1 of this fractional part. Then on this side, I can square it. So it's a minus. The square of the first is x. And then there's the double product, which is plus twice the square root of x times the fractional part of the square root of x. And then there's a minus the fractional part of the square root of x squared. Okay. And now, well, first, let's put something on one side. So on this side, we have 2x times the sum for n goes from 1 to the square root of x, 1 over x, and 1 over n. Then I have a minus x. And then let's look at these leftovers. Okay, so I have this bit here, I have this bit here, and I have this bit here, right? So remember that the fractional part of a number is always smaller than 1. So each of this argument of the first sum is smaller than 1. And the number of terms on the first sum is the number of terms is square root of x. So if I write this in the form of an error term, then what I have is that the error term, well, it's certainly lesser or equal. So this is negative, but let's bound it with its positive part. So this is 2 square root of x. Here I have also plus 2 square root of x. And here I have a minus 1. So altogether, e of x is bounded by a constant times square root of x. So the sum of d of n less or equal than x is equal to x times 2 sum for n that goes from 1 to square root of x of 1 over n minus 1 plus an error term of the order of square root of x. So this is where we got so far. Okay, now we use the lemma. The lemma that says that the sum for n from 1 to, say, capital T of 1 over n, this is equal to log P plus gamma plus an error term of the type 1 over T. So if I use it there, if I take this and I plug it in here, we get that the sum for n less or equal than x of d of n is equal to x times twice. Well, this is log of the square root of x plus gamma plus an error term of the type 1 over square root of x. And then I have a minus 1. And then I close the bracket. And then the other error terms of this type. Okay, now I can just write this as, log of square root of x is 1/2 log x. So it's x log x. Oh, sorry, I also have another bracket here. Then I have a plus 2 gamma minus 1 times x. And then I have a x times O of 1 of square root of x. Well, it's very easy to check that all the error term is of this sort, which is what we wanted to prove. Okay, so this is the end of the proof of the Dirichlet hyperbola theorem. which says that the average of the divisor function admits this asymptotic formula. And, I only use the tools from calculus. So my suggestion is to try and go over it by yourself, just doing all the calculation, check my calculations, and I'm certain that it will give you a certain satisfaction to be able to do it with your hands. But there's nothing complicated about this proof. It's only sums and partial summation formula, but the knowledge you achieve by studying this, it's quite significant. Okay, then I want also to state another theorem, which I don't want to prove. The proof is it's not too complicated. It goes along the same line, but it's nice to see. So another theorem without proof. Very, very similar proof. And the statement is a statement about the sum for n less or equal than n of sigma of n. So this is the number of divisors of n. Okay, and the theorem, so the theorem says the following, that this is equal to the following constant, surprising to me it here, pi squared over 12 times x squared, and then an error term of the type x log x. So this is telling us that on average, so let's write, this is good to write, I think. On average, sigma of n, on average, sigma of n is about pi squared over 12x. So what I mean on average for n less or equal than x, sigma of n is about, so pi squared, so pi squared is pi squared is around 9, it's more than 9, right? So this is what it's telling you, that on average, this is the value. Okay. Okay. Now there's a, talking about arithmetic functions. There's another function. I also promised you that I was going to talk more about the Euler phi function, which I'm not sure I'm going to have the time to do, because I am strongly convinced that you cannot resist more than 1.5 hours. But there's a function that I have to talk to you about. It's called the Möbius function. So this is again an arithmetic function. So mu of n. So it is an arithmetic function. And so here's the definition. The definition is a bit artificial. So the first time one sees this definition, wonders if it's the product of some complicated idea. But I hope in a little while you will agree with me that this is very natural. So first of all, the value of the function is 1 if n is equal to 1. Then it is minus 1 power r if n is the product of PR are distinct primes. And otherwise 0. Okay, so let's write the number 1, 2, 3, 4, 5, 6, 7, 8. Oops. 8, 9, 10, 11, and 12. Okay, so here there's n. Here I want to write mu of n. Okay, so mu of 1, we agreed it's 1. So
Yes.
mu of 2, what is mu of 2?
-1.
-1. Mu of 3?
-1.
-1. Mu of 4?
0.
0. So 5, -1. Mu of 6, this is the product of 2 primes. So this is 1, -1,
0.
0,
0.
0,
1.
1,
-1.
-1,
0.
and 0. So these are the values of the mu function. Okay, the first few values of the mu function. So there's another way to define it. So suppose we consider the following two Dirichlet series. So definition. Let's take the following infinite sum. The sum for n that goes from 1 to infinity of 1 over n power s. This is called the Riemann zeta function. And this is going to be the topic of Michel Waldschmidt lectures next week. Okay, so I'm not going to tell much more about this, except that these make sense for s bigger than 1, right? Otherwise, the series does not converge. And then let's take another series, which I'm going to call f of s, which is done in the following way. Sum, where n goes from 1 to infinity, of mu of n over n power s. Okay, and I'm not going to give a name to this because in a second you will understand what's happening. Then I want to take f of s, and I want to multiply by zeta of s. This is what I want to do. And what is the result of this multiplication? So this is the sum for n goes from 1 to infinity. And then there's a sum for m that goes from 1 to infinity. And then I have 1 over n power s. And then I have mu of m over n power s. This is what I have. Okay. And then what happens here? Well, let's see. So I can write it in the following way. So this is the sum, both of m and n, both from 1 to infinity. And then I have a mu of m divided by m times n to the power of s. Okay, so I can also rewrite it in the following way. So this is the sum for k that goes from 1 to infinity, and then the sum for all pairs m and n. So these are all possible natural numbers such that the product is exactly k, right? And at this point, I can put 1 over k to the s here, And here I have a sum of mu of m. Right? This is exactly what I have. Okay, and therefore, what is this equal to? This is the sum for k that goes from 1 to infinity of 1 over k power s. And here inside, so inside I can write this is the sum of what? So this is the sum for all m dividing k of mu of m. If k is fixed and m is a divisor of k, then n is uniquely determined, right? Okay, so the question is, what is the value of the sum of m dividing k of mu of m? Well, let's make one observation. The first observation is the following. Mu is a multiplicative function. So mu is multiplicative. Why is it multiplicative? Let's check the definition of mu. So we go back to this definition. Okay, well, mu of n times n, right? So mu of n times m. Okay, so the question is this equal to mu of n times mu of m when n and m are coprime? Well, if both mu of n is equal to -1 to the s and mu of n is -1 to the r, so when n is the product p1 ps distinct and m is q1 qr distinct, if this happens, then there are no primes in common. So mu of mn is -1 to the r plus s, right? Because the product is going to be the product of s plus r distinct primes, and this is equal to mu of n times mu of n. If either mu of n or mu of m is 0, then mu of n times n is also equal to 0. So mu is multiplicative. Okay, which means that the sum for a m dividing k of mu of m is multiplicative. This is something we observed yesterday, that if I do the sum of divisors of an arithmetic function, I get again an arithmetic function. Now, the sum of m dividing a power, so if we call this, say, g of m, so g of p to the a, it's the sum for m dividing p to the a of mu of m. Well, the divisor of p to the a is 1 p squared, etc., all the way to mu of p to the a. So this is 1 minus 1 plus all zeros. So this is always equal to 0, right? Well, g of 1 is 1, right? Because mu of 1 is 1. So the conclusion is that the sum for m dividing k of mu of m, so this is a multiplicative function. So it's the product of its values on prime powers. But on prime powers, we have checked here, is always 0. And so this is 0 for m different from 1, and this is 1 for m equal to 1. Okay, so let's go up to check where did we need to make this calculation above. So we go up above, and we needed to make this calculation here, right? And this was equal to this. So we needed this calculation when we multiplied zeta of s times f of s. That we obtain, this is equal to the sum for k goes from 1 to infinity of 1 over k power s times the sum for m dividing k of mu of k, of mu of m, right? We needed this. And here, f of s is the sum for n that goes from 1 to infinity of mu of n over n power s. Okay. Now, we just deduced that this is always 0 if k is different from 1. So this coefficient inside is always 0 except when k is equal to 1. So at the end, we obtain the identity that f of s times zeta of s is just 1, which is equivalent to say that the sum for mu of n over n power s is equal to 1 over zeta of s. Okay, well, this is a very important identity, right? Which is also telling us that the mu function is not coming from nowhere, right? The mu function is very natural. The mu function is the coefficient of n to the s when we write the inverse of the Riemann zeta function as a Dirichlet series. Okay, so we could have defined the mu function starting from this identity, right? But it would have been much more complicated to deduce other properties. But so you might need this formula next week when you work on the Riemann zeta function with Michel Waldschmidt. Okay, so an important property of mu is the Möbius inversion formula. So the Möbius inversion formula is the following theorem. So suppose that f is and g are arithmetic functions, and that f of n and f of n is equal to the sum of d dividing n of g of d. So f is sometimes one calls it the Dirichlet transform of g. So sometimes one may say that f is the Dirichlet transform of g. Well, then, if this is the case, then g of d is equal to the sum, g of n it is equal to the sum for d dividing n of the Möbius function of d times f of n over d. And it's actually, this is an if and only if. So this is the statement of the Möbius inversion formula. Okay, so if f is the Möbius transform of g, then I can recover g from f using the Möbius formula in this fashion. So rather than proving this, this is proof is simple. Proof is not proof, not hard. I would like to give you an example of this. So let's, just because I want to conclude talking about the Euler function that you met already. So if phi of n is the number of k less or equal than n, which are coprime to n, we know that every integer k between 1 and n has GCD with n. From this, we deduce that, so phi, if I take the sum for d dividing n of phi of d, okay, so this is the number of integer which have GCD with d equal to 1. Well, it's quite simple. I don't know whether you covered this in the other classes, but this is very simple to show that this is equal to n. Maybe you can confirm whether you've seen it or not, but it's very simple to prove this. Well, from this, we deduce the formula. From the Möbius inversion formula, we get this formula for phi of d. Phi of d is equal to, sorry, phi of n again. Is the sum for d dividing n of mu of d times n over d, which is exactly the application of this formula to f equal the identity function and g equal the Euler. So these are, it's done with f equal the identity function and g equal the Euler phi function. We get this identity here. Okay, and from this identity, with along the ideas of the Dirichlet hyperbola method, there is another formula which I'm sure you will like. So theorem. We're not going to prove this, but the proof is also very similar to the one above. Is the average value of phi of n. This is equal to 3 over pi squared x squared with an error term of the type x log x. So this is the average value of phi. Not difficult to prove. Okay, so this is what I wanted to tell you. I want to finish just giving you a reference where you can study these lectures that I gave you. And so the reference is William, so references. So on the web, this is the William Chen notes on elementary number theory. In chapter 2, is devoted to arithmetic functions. Okay, so this is and it's enough you go on Google and you write William Chen notes on elementary number theory, and it will bring you to a page where you can download the pages you need. These are extremely well written. So now it's 11:42. I think it's a good time to stop, because I think you're tired already. So I'm back here. I would like to thank you for your attention. In case you have questions, I'm here to answer. And otherwise, I wish you luck for the remaining part of the school. Again, I'm very sad not to be with you in Yogyakarta. It's such a beautiful place to be, and I wish I will come back soon to visit you. Okay.
Okay, so please give a warm applause to Francesco. Okay, so is there any question maybe from the offline participants or online participants? For the online participants, you can write the question on the meeting chat, or you can ask for Francesco directly.
Okay, I will be attending. If there are questions, you can also write an email to me.
Yes.
And I will answer as quickly as possible if needed. Okay.
Okay.
So I guess it has been another long day for you guys. So take some rest.
Yeah.
And go on tomorrow. Okay. So,
Okay.
Karen, bye bye.
Once again, thank you, Prof. Francesco, for giving the lectures to us. Okay, so once again,
bye-bye.
please give a round of applause to Prof. Francesco.
Okay, thank you. Thank you very much. Okay, bye-bye.
Bye. Thank you, Prof.